Hello, Seahawks. Video 9, Part J. We're going to talk about R squared. And this is going to be a good one, I can tell. Super important concept. We're still evaluating the quality of our regression equation. Okay? Not all regression equations are created equally. Some are better than others. And your common sense has to tell you that if the points are very close to that regression line, then it's probably a good model. And if the points have lots of scatter about the regression line, then it's probably not as good of a model. We'd like to quantify that. Okay? And how will we do it? We'll use those residuals, and using those residuals, we'll come up with a statistic that will sort of quantify how good our regression equation is. Let's recall the formula for residuals. Every data point in our regression analysis will have a residual. We'll recall the formula. Residual equals the observed y value minus the predicted y value. So we had this way back at the beginning of this whole chapter. This is how we create the regression equation. So it seems like a good place to sort of evaluate our regression equation. In symbols, we can use the letter E for residuals. That's just a shortcut for errors, residuals, errors. And the observed y is just y straight up. Predicted y is y hat. So here's the formula. E equals y minus y hat. All right, what's the mean of the residuals? Well, some points are above the line. Those have positive residuals. Some points are below the line. Those have negative residuals. They'll always cancel each other out. Bunch of positives, bunch of negatives. The mean of all the residuals will always be 0. And remember, we're going to use the residuals to evaluate how good of a regression equation we have. Because the mean is always 0, I really can't use that mean for anything. No matter what the data look like, the mean is 0. So we'll turn to the variation, right? It's the variation in the residuals that will be the key to assessing our model. Think of a scatter plot. If the if the data points are very tight to the line, there's not a lot of variation as my hand goes up and down here, right? That's probably a good regression equation. If the data points look like this, lots of variation, in your head you can say, well, that regression model is probably not going to be very valuable. All right? So we're going to look at the variation of the points about the line. I'm going to give you the formula for the standard deviation estimate. I'll tell you right now, we won't use the formula. When we run a regression on StatCrunch, it will spit out this number, but for those that like this sort of thing, here it comes. We'd like to measure the variation of the residuals by estimating the standard deviation. S, standard deviation, subscript E for the errors. Standard deviation of the errors equals, all right, big square root, sum up the E squareds, divide by n minus 2. So big square root, under the fraction up top, sum up the E squareds and divide by n minus 2. We're dividing by about how many data points we have, so this is sort of like an average, and this is just the residual, so how far each data point is above or, below the line. All right. If there's one formula, you'll probably never use the MAT127. This is the one. Let's think about it, though. Just because we won't use the formula does not mean it's not important. It is important. All right, so fill in the blanks. How small could that number be? Think of the data points. If your data points are exactly on the regression line, there's absolutely no variation. As you move left to right, the points fall exactly on a line. That number would be 0. No variation of data points about the regression line. Data points will fall exactly on a straight line. That's the best case scenario. But again, when you collect real data, you're not going to have this. But it does clue us into what we want. We want this S sub e to be very small. In fact, the smaller the better. Next bullet point, if the data points are tightly packed around the regression line, then SE will be small. When SE is small, we'll have more confidence when using our regression equation to make predictions. Quick example, I've got a little space here. If I just draw that regression line, here's my data points. Right. Data points very close to the line, not a lot of variation, then S sub e will be small. We would have a lot of confidence using this regression equation for prediction. Opposite case, of course. Not all data sets look like that. If the data points are very scattered about the regression line, S sub e will get big. S sub e will be large. If that's the case, then we will have less confidence using the equation to make predictions. So, of course, here's our regression equation, but the points look more like this. Maybe there's a linear positive pattern here, but the strength is much weaker, right? So there's lots of variation about the line. S sub e will get big. Use this equation to make predictions. We're not going to feel so good about it. So the problem is what's big and what's small. Here's where things get tricky. We cannot just look at that number in isolation. Oh, the number is 2.2, must be small. Or the number is 1,502, must be big. We have to put that number into the context of the data set. So here's where things get tricky. We're going to compare the variation in the residuals, so about the line, and we're going to compare it with the total variation in Y. So here's the total variation in Y. Now compare it to the variation about the line. And we'll look at that ratio to determine if we have a good regression line or not. Neighborhood data set. Hey, at least it's not direct loans. Let's take a look. Do we flip the page? I guess we do. Well, I guess you did. Example, neighborhood data sets. We've been looking at this off and on. We'll use square footage of a house to predict assessed value. Below are the relevant standard deviations along with the scatter plot. So let me see what this next slide looks like. All right. I've got two numbers here. Remember, assessed value, this is Y. And residuals, if you want to put a variable name, we'll call that E for error. So Y and E. Standard deviation for Y, 36,736. Okay. This is the total amount of variation in all the houses when I'm looking at assessed value. Whole scatter plot. Standard deviation of the errors, S sub E, 15,000. This is the amount of variation just about the line. We'll go back to the previous slide and sort of make wild hand gestures here. If we look at the scatter plot, how much variation in Y? So here's the Y variables, right? The data values. That's the 36,736 number in terms of how much variation in Y. I can put a horizontal line at Y bar and try to figure out how much variation. The 15,000 number is, once I've put that linear model in, how much variation, still going up and down here, is about the line. And so about the line is the 15,000 number. Total is the 36,000 number. And now we're going to look at the ratio of those two numbers. Down at the bottom of your sheet, doesn't have a letter there, but it says put into words, what the heck does the 36,736 mean in the context of the problem? All right, S sub Y equals 36,736 is the total variation as measured by a standard deviation. So the 736 is the total variation in y equals assessed value. You could say one last thing. It is it's the typical distance, or the average distance, to the mean assessed value. I don't know if I have the mean assessed value. I don't, but it was probably about 200,000 or somewhere in there just looking at the picture. Okay, so on average, in that neighborhood, a home price is probably 200,000, 210, 220. And on average, there's the average distance to the mean, about 36,700. All right, next part. It did change. It's the one at the bottom. Put into words what that value 15,101 means. Okay, so S sub E equals the 15,101 is the typical vertical distance from each data point up or down to the line. So the 15,101 is the typical vertical distance from the points to the line. If that number is big, then the points on average are far from the regression line. If that number is small, then the points on average are typically close to the regression line. Okay? So we need to look at the ratio of these two. Flip over to the next page. Hang with me, students. This is tricky to teach as well as tricky to understand, so we're all in the same boat together. If the relationship between square footage, which was x, assessed value, which was y, was perfect, then S sub E would be 0. If the relationship was perfect, it would be 0. All the points would be exactly on the line. This means that if you told me square footage, say I have this house, it's 2,000 square feet, I could exactly predict how much that house is assessed at. It's like saying that the county only uses square footage to predict your tax bill. Nothing else goes into your tax bill except the exact square footage of your house. Okay? That's not the case. What if the opposite case, complete other side of the coin? If our linear equation was entirely worthless, how big could this S sub E get? Now, it can't blow up to infinity or anything like that. It's capped. The biggest this S sub E can get is S sub y. How much variation is there in y? Now that I've created that linear equation based on the data, if that linear equation was worthless, then I wouldn't have removed any variation. So if it was worthless, S sub E would equal S sub y, which is that 736. Completely worthless. This means that square footage has no predictive value for assessed value. It means you tell me that a house has 2,000 square feet and I have no idea what the tax assessed value might be. No predictive value whatsoever. Okay? Now, these are the two extremes. Perfect relationship, S sub E would be 0. Worthless relationship, S sub E would max out at S sub y, the 36. Now, of course, in almost all situations, you'll be somewhere between the two extremes. And depending on where you fall between the two extremes tells us how good the regression model is. It'll fall somewhere between perfect and worthless. Okay, so here it comes. Obviously, students, in nearly all real-world situations, real data situations, will be somewhere between the extremes. What we'll look at is the ratio of the two, S sub E and S sub Y. Look at the ratio. We'll gain an understanding of how well the linear equation fits the data. So, here's where it might get confusing. Out of a total amount of variation of S sub Y, 36,736, the linear equation left out the variation in the residuals, 15,101. That means, what did the linear model account for? Well, 36,736, subtract off 15,101. The model accounted for 21,635. We're looking at the variation in Y accounted for by the model. We'd like this number to be big. We'd like this number to be small. One's based on the other, so if we've got one, we've got the other. Okay. Now let's turn this into a fraction. One little note, FYI in statistics, we often use squared units. It just makes the calculations easier, believe it or not. So think back to when we calculated standard deviation and think of when we use least squares. In both cases we use squared units. We'll do the same thing here. It's for technical reasons. We're going to square those standard deviations. If we do that, they're now called variances. Almost to the bottom of that page there. If we take the variance of assessed value, what do we get? Well, what we'll end up doing, we'll end up squaring S sub Y. And if I square S sub Y, that's the 36,736 number, and that gets squared, becomes a really big number. I'm going to give it to you. Here it is. This is about, 1,349,533,696. So 1,349,533,696, about 1.3 billion. Okay, that's the variance for the Y value, which was assessed. We're going to do the other one now, down at the bottom of the page. If we take the variance of the residuals, what the heck do we get? So leave that one there. I will square S sub E. S sub E was the 15,101 number. That gets squared. It's going to be a big number again. This one looks like 40,201. Very technical video. We do need to get through it. Basically, remember, we're looking at the ratio of S sub E to S sub Y. The only reason we're squaring is because, believe it or not, it makes the calculations easier. Okay, so here's those two figures. We'll flip the slide. We're on the last page. We've almost made it to the end here. You've got to pause at home, so we're going to clean this up. Top of that last page, looking at the ratio of variances, those squared standard deviations, we can get the percentage of variation in our Y variable not accounted for by the linear equation. Here it is. If I take S sub E divided by S sub Y, remember this whole talk was based on, is this a big or small number? Now I'm comparing it to the total variation, and now I'm squaring it because it makes the calculations easier. S sub E over S sub Y squared. I can push that square inside. These are the two huge numbers from the last page. I'll write them out just for completeness. Up top, 228,040,201. Divided by, down below, 1,349,533,696. 696. Looking at the ratio variances, we can get the percentage of variation in Y not accounted for by the linear equation. If you divide this out, remember we already squared these already. Turns out this is 0.169, or finally, the longest probably calculation of the semester, at least getting there, 16.9%. If the linear equation is doing a good job describing the linear relationship between x and y, then this percentage should be what? We're looking for the variation not accounted for by the linear equation. This percentage will be small. Last step, I promise. If that's the percentage of variation not accounted for by the equation, it's easier to think of, well, what was accounted for? All we'll do, we'll take 100%, we'll subtract off the 16.9. We'll finally arrive at this most important number for linear regression. And then we'll worry about interpreting the thing. Okay? So the fraction of variation in our y variable that is accounted for, it's called r squared. It's called r squared like this, usually capital R, I'm not even sure why, but it is. Squared on software, sometimes you'll see it like this, RSQ, because I think it's hard for software to print the superscript squared. So r squared equals, I'll take 100%. I will subtract off, I hope, 16.9%. Don't know if I've forgotten that number, but, good. 100 minus 16.9 is about 83.1%. So I don't know, I'm guessing about 22 minutes into this video, we finally get the answer we're looking for. 83.1% is the total variation in y that is accounted for by our model. If the linear equation is doing a good job, students. If the linear equation is doing a good job describing the relationship linearly between x and y, this percentage should be large, big. Bigger is better. I guess that could max out at 100%. It'd mean that the points are exactly on the line. The worst that can get is 0%, and so we're at 83%. Feels pretty good. All right. You have to interpret it, then we're done. For the neighborhood data set, we interpret r squared as follows. What is it, 83.1? 83.1% of the variation in our y value, our y variable. What the heck problem are we even doing? Oh, neighborhoods. 83.1% of the variation in assessed value is explained by knowing a home's square footage. (83.1% of the variation in assessed value is explained by knowing a home's square footage. Pretty good. What's left over? That's 16.9%. 16.9% is explained by other factors. And I know it's a long video, but I'm just dying to ask you, like what? So if I know a home's square footage, I can explain about 83.1% of the variation in y, which is what we're trying to do with a linear regression analysis. That's leaving about 17% unexplained or explained by other factors. What other things might help you assess a home's value? I mean, there's certainly lot size, how big the property is besides the house. There's certainly maybe sales price. Could be some categorical variables like neighborhood, for example. And I ran out of space, so etc. Knowing square footage of a house does a pretty darn good job of explaining its assessed value, but keep in mind there are other things, right? Lot size, sales price, neighborhood. That would help round out, get us closer to 100%. We did it. Next video, we'll practice with some other scenarios interpreting this number, this R squared. Every regression analysis you do, this number is going to be one of those numbers that we'll concentrate on. All right, so way to hang in there. We'll see you in class. Thanks for watching.